And first, thank you for the organizer to let me the opportunity to present you first works about the shell construction of during embryonic life of Sepia officinalis, which is first results of my postdoctoral contract. So first, I have a little more. First, all studies about mollusk biomineralization show that we can find among mollusks a very important diversity of structure and regulated by very various and complex mechanisms. But most of them are realized until few years was realized on only two genus. A bivalve genus, the genus Pinctada, sorry, with the pearl oyster, and the genus Haliotis, the gastropod, known also to build a necker. But we have no information or very few information about other group of mollusks, including cephalopod. Recent studies described the protein constitution of the shell of the ancestral cephalopod Nautilus, but until now we have no information of the setup of the intern calcareous shell of Sepiidae as the cuttlefish Sepia officinalis. First of all, I will present you what we know about the microstructure, because it has been well studied a few years ago, before to begin about the formation of this structure. First, the composition is around 90% of inorganic matrix with 100% aragonite and 10% of organic matter, with a large amount of beta-chitin and also a high quantity of unknown proteins. Here you have both pictures in the cuttlebone or cuttle shell, I prefer, in ventral view, and here in the lateral view in the animal. And the two parts are particularly interesting us today. The dorsal shield, which is here in green and here in the dorsal part, and the phragmocone here in yellow. The phragmocone, as you can see here, is a superimposition of chamber which are built during all the animal of the life of the animal. Sorry, and each of these chambers have an opening at the anterior part of them, which form this striated area called the siphuncular area, and which allowed to the animal to regulate its buoyancy by fluctuating the gas volume present into its shell. This is the structure in the scanning electron microscopy. Here you can see the dorsal shield, and here is the phragmocone. You can observe the two very different structures, and if we here you can observe the septa, which delimited horizontally a chamber, and these septa are connected by pillar vertically, and these pillars are interconnected by hole. You can see better here, which is a top view of a chamber, and you can observe that all pillars are connected by hole, forming this strange structure, not well characterized. If we focused on the insertion of pillar into the septa, we observed a chamber floor here with a columnar necker structure, and a chamber roof with a prismatic layer, and also organic sheet in all of which recover all the part of this mineral structure. Here the presence inside of the septa of organic matter is again debatable. So we asked the question of how this complex structure is set up, and this is why we decided to work on the development of this during early life stages, because at this period the shell growth is very fast, and we could also potentially observe modifications due to the transition between the environment into the egg and the external environment. This approach is possible because of the direct development of Sepia officinalis, and also because of the same mode of life of juvenile than adult. And briefly about the development, there are 30 stages during the Sepia officinalis development into the egg. Between the stage 18 and 22, you have the formation of the shell sac by the mantle in dorsal position, and from the stage 23, when the shell sac is closed, you have the formation of a primordium, and then the shell. From the primordium is composed in the first time of a high amount of beta-chitin, and then calcification occurs on this primordium to form one chamber per stage until the stage 30, when hatching occurs, and when we have 6 chambers. So we ask what if the mineral composition of the shell was the same in the embryo than in adult, and we would like to we begin to investigate to realize investigation to know how and when structure previously presented were set up. First, to study the composition, we use a stage 25 shell, so just at the beginning of the mineralization, by X-ray crystallography analysis, and as you can see, observe here with a different profile. The green one is aragonite, the blue one is calcite, and the other one, the red and orange, are shell, embryo shell. We observed not the same peak than with calcite, and similar peak in different parts of this profile that aragonite. This profile is the same than those previously observed and published from adult shell. So this analysis allowed to think that it is aragonite at the beginning of the shell formation. Then we investigate three-dimensional structure with on 2 stages, stage 30 and intermediate stage, to have an idea of what's happened between in the transition during the transition between one chamber and the following one. So here you have in the 3-dimensional with the anterior part and posterior part, an anterior part of this shell stage, of the shell corresponding to this stage. Here is so you have 3 chambers closed, 3 chambers, and here you have the chitin which begin to be formed before mineralization occur. But CT scan allowed also to observe into the shell. As you can see here, we are at the extreme posterior part of this shell, just here, and we can observe all the pillar and the ventral part of the shell that we can see very much. The first thing which was we observed was the non-connection of all the pillars between them, as as described in adult here. So we have here stage 27, 28, and stage 30 in dorsal part and inside of the shell, and no connection appears, even if we have an elongated part, but nothing similar with that. Then we observed, here you have again a lateral view of of this shell with the posterior part and the anterior part. Here you can observe during this transition phase the dorsal growth of the dorsoventral growth of pillars with branching to the extremity of them, as you can see after calcanein incorporation in this picture. And you can see also here this branching, few observed before. And last observation we realized was, I don't know if we see here, but the vision is better here. You have an anterior-posterior growth of this formation of the pillars at the beginning of the chamber formation, that you can also observe here, because here pillars are not begin to grow. And this first observation allowed us to understand a bit more how the Sepia officinalis shell formation occurs. With first an organic layer, our observation were used with data from the very interesting article from Bundel and Bolski. So first you have an organic layer, which is the original, at the place of the original septa. Then an aragonitic prismatic layer is formed in the dorsal part with the formation of pillars and branching at the extremity. But afterward, we don't know exactly what's happened. We don't know if the columnar nacre layer observed here is the result of the mineralization in the following process of pillar mineralization, or if it's the organic layer below which induced this mineralization. And we don't know also when exactly the hole are formed, because they are not present at hatching time. It could be it probably have an importance for a newly hatched juvenile, because it could be influenced their behavior and their swimming behavior, because they have the same possibility to regulate their buoyancy. And we would like to complete all this preliminary work by measuring pillar density to know if the growth of chamber of all pillar formation stop when the chamber is finished, or if it's a process which continue. And we also would like to analyze other shells from post-hatching animals to determine when whole are formed. And we have next work. We already begin next work, which consists of first study of proteins involved in the cuttlefish shell formation in adult stage, and also, if it's possible, in juvenile stage, by coupling proteomic and transcriptomic analysis, and by differentiation of the dorsal and the ventral part, because our preliminary studies highlighted quantitative and qualitative differences between the protein content of the dorsal shield and the phragmocone. And transcriptomic analysis will be realized on the dorsal and ventral part of the shell sac to complete this data on this genomic unknown model. So thank you for your attention. I would like to acknowledge the founding ATM Interaction Mineral Vivant, our physicist colleague, and the platform Asterix for the CT scan images. Thank you very much.